What we're going to be doing today is looking at actual applications of using the derivative. Okay, if you remember, the derivative itself has a couple of different meanings. Some of them are graphical, some of them are related to the way quantities change. Okay, so the graphical meaning of the derivative is it's the slope of a tangent line to the graph of your function at a particular x value. Okay, and that slope changes as you go around the graph. Okay, another meaning of it is it's the instantaneous rate of change of your function's output at a given x value or a given input value. I hate using the terms x and y, even though everybody's familiar with those, because again, your variables aren't always going to be x and y. Okay, sometimes it's going to be t and s of t. Okay, so it's important to look at your function, the words, and decide what's the input quantity, what's the thing I can change or that changes all by itself, like time, and what's the output quantity, what's the value that's dependent on that input value's change. Okay, so there's a whole lot of algebra stuff going on in the background here, which is why a lot of students find calculus difficult. It really isn't. It's extremely formulaic, but because it depends on a lot of the algebra you've already learned, there's a lot of stuff going on at once. Okay, so what I would tell you is don't get discouraged. Okay, it gets clearer the more you practice it. Okay, and again, what you're going to use it for is pretty much like the stuff we're going to talk about today. If you see a business situation and you have function models of your things, that's what you care about. Okay, nobody's going to give you an f of x and ask you for its derivative. That will never, ever happen in the real world. Okay, but they may ask you, hey, when we change our production level to 2,000 a month, how fast is the cost changing? Okay, that might be a real business question. Okay, so let's quickly, I'm going to share my browser with you so you can see where we are. You can see we're currently in week 6. Okay, and what we're going to be doing this time is we're going to do rates in real life. So I'm going to be using the rates in real life notes. Okay, and next time we're going to talk about using another method to find high and low spots in our graphs. Okay, so since the derivative is tracking the slope of that tangent line as we go around the graph, you might remember we're interested in where the tangent line's horizontal, because that's where the graph is going to turn around. So it'll either be a high spot or a low spot, and it'll tell us where our function reaches a maximum value or a minimum value. I might be interested in that as a business person because I might care about a minimum cost or a maximum profit. Okay, so that's kind of what we're going to be talking about today. All right, and next time we're going to learn another strategy for finding those places. Okay, so I'm going to be using rates in real life notes, and just give me a moment to get that open and I'll share it with you. Okay, let me share that screen with you. Okay, so now everybody should be seeing rates in real life examples, which is what we're going to be talking about. I'll open up the chat in case anybody wants to ask a question while we're going along. But again, I'd encourage you to please just unmute yourself and ask a question. Not only is that faster and less clunky, okay, but it kind of, makes it more like a real class rather than me just yakking up here, okay? So the first thing to understand, and you may have learned this when you took introductory algebra, but real world rates have a unit in them, okay? You might remember from introductory algebra that you computed slope, okay? Slope is an average rate of change, and in a real applied problem, the slope has units. It has the output or the y units on top, and it has the X or the input units on the bottom. Well, the same thing is true when you take a derivative, okay? It's going to have output units on top, okay, whatever your Y units are in, or your output units, and it's going to have input units on the bottom. That's why it's so important when you set up a real world problem to think about what's the input, what's the output, and what units are they in, okay? Because again, if you're trying to figure out an answer to a real world problem, you want to know what is that number. The rate isn't just 6, it's 6 something, okay? It's 6 miles per hour, or it's $6 per cell phone, or it's whatever it is that we're interested in, whatever our input and output units are. Okay, so here are some examples, okay, just to get you used to the idea, okay? So if you're interested in the change in your f of x, your output, okay, with respect to changes in your input. Now, this with respect to is an important concept in calculus and in rates in general. What that means is, how much does the output or the y value change for one step in the input value? Okay, so you think of these as two quantities that change together. Okay, so namely, your y values may be going up as your x values are going up, or your y values may be going down as your x values go up. Okay, they don't have to always go in the same direction. The important thing to understand is they change together. Okay, that's what the with respect to means. It shows you the linkage between the output value and the input value. Okay, now you might be sitting here thinking, yeah, what's the big deal? My input value is X. I know that's always going to be, you know, the with respect to. Not necessarily, okay? Not in this class, but in other classes and in real life. Sometimes your output value can change with respect to a number of different inputs, okay? So you're used to functions where there's only one input value. And what I'm telling you is there are models out there, like joint cost models, for example, where you've got more than one input value. So that's why it's important to get the with respect to an input variable straight, okay? Because again, in other applications, you'll have a choice. It won't always be X, okay? So again, here's some examples in this table, okay? Remember, if I have a derivative, okay, my units are my f of x units on the top divided by my x units on the bottom. Okay, why is that? Because this is the form of average rate of change or slope, right? y2 minus y1 over x2 minus x1. And it's also the units that would go in that limit definition of the derivative. Remember, f of x plus h minus f of x on the top, and the difference of x plus h minus x on the bottom. Okay, so it's important to realize these are our rate units. Okay, so if I'll do the first one here, the units of my rate, my derivative, if my x units are hours and my f of x units are miles, is miles per hour. Okay, and it's again, the divide sign is read as per. Okay, the word per or that divide sign tell you you have a rate. Okay, everybody comfortable with that? Okay, any questions so far? Any questions so far? Again, unfortunately, it's been a practice in a lot of math classes for students to focus on just getting the numerical answer and not worrying about any of the words. I hate to break it to you, but the words are actually more important, okay? Because we can leverage the calculating or a lot of it off to a calculator, Okay, so understanding the words becomes crucial, particularly in business. Okay. So let me ask you, and again, either type your answer in the chat if you're comfortable doing that, say it out loud. Okay, what are the units for the second row in the table? What are the units in the second row for f prime of x? Okay. Okay, so we have our output units, automobiles per person or per people. Okay. So in other words, if we're doing this function has output units in automobiles, its input units is people. Okay. So the rate would be output units, in other words, automobiles per person. And in a country like the US, that number is probably bigger than one. Okay. Particularly when you think of all the fleets that are out there, as well as people who own more than one vehicle. Okay. How about the third one? Okay, third row, what are the units here?
Pancakes.
Okay, pancakes per what?
$1.
Thanks, Brunella. Pancakes per dollar. You might imagine that being a rate I'd be interested in if I were, say, making pancakes in a restaurant, or even maybe making pancakes to give out at some sort of a function. How many pancakes can I make per dollar? Okay. All right, how about number 4 or fourth row? Somebody else want to give it a try? What are the units here?
Isn't it gonna be like trout per days?
Yep, output trouts or trout per days. Trout is one of those weird words that's singular and plural. We don't say trouts. It's trout for one fish and trout for a bunch. Okay, so how many trout can you catch per day? Okay, how about the fifth one? Again, I want to make sure everybody's super comfortable with this before we start the applied problems. This one's a little weird. Give it a shot. That's this row.
Isn't it miles per second per second?
Yep. Okay, so miles per second. Okay, I'm going to go down here and show you this one. I have miles per second as my rate on the top and seconds on the bottom. Okay, this can be rewritten like this because my seconds here is in the denominator of the numerator. It's like doing this, miles per second. Seconds. See the 2 seconds down there? Yes, miles per second squared. You might think of this as a velocity or a speed, right? Miles per second. How fast is the baseball going, or whatever it is, the bullet probably, okay? Or maybe even a satellite, okay? Miles per second, something that travels really fast, okay? And if you want to know how fast its speed is changing, well, then you're asking about a quantity called acceleration, okay? And acceleration can be either positive or negative, okay? But again, the rate of change of speed or velocity per unit time is called acceleration. And that's measured in these units, okay? So it can be miles per second squared, it can be meters per second squared, it could be feet per second squared. The trick is when you see that second squared in the bottom, it's a giveaway that you've got an acceleration quantity, okay? So in some cases, the units can actually help you solve the problem, okay? If you recognize them as, for what they are, okay? How about the 6th row, the one with seconds as input and gallons for output? Anybody want to try that one?
Is that gallons per second?
Yep. Okay, so again, we might be interested at the rate at which a pump pumps out a tank or a pool. Okay, how many gallons per second? Okay, so we'd be interested in that rate. And let's do the last line, the last row. Okay. Anybody want to try that one? Okay. Again, output units divided by input units.
Test points per study hours?
Yeah. Test points per study hour. In other words, maybe somebody is trying to do some research on whether or not there's any difference in how many points you earn on a test depending on how many hours you study. Okay, so how many test points per study hour. Okay. Great. Okay, so basically, I think you've got the general idea of how the units play out in a rate problem, which is going to be a derivative problem in our case. Again, keep that in your mind. If they're asking you for a rate, okay, or if they're asking you for a marginal, put that down here. Okay, rate of change. And unfortunately, your book doesn't make the distinction. It won't say average rate of change, instantaneous rate of change necessarily. They may ask you what's the rate of change at a particular input value. If they're asking you for at a particular X, a particular input value, they're asking you for a derivative, because remember, if they wanted an average rate of change, two input values would need to be involved, right? Because you need a C count line between the two input values. So if it's at a particular input value, you want a derivative. And also if they're asking you for the marginal value at a particular input value. Okay, because again, marginals, again, my accounting majors probably have a better definition than I do, but the way I think of marginals, like for example, if I'm talking about marginal cost to manufacture a product, I want to know at this particular manufacturing level, like I'm making, say, 2,000 of these. If I make the 2,000 first, how much will my cost change? Okay, so it's the change in your output for making and selling one more thing. Okay, that's your marginal value. Well, that's exactly the same thing as the rate of change, the instantaneous rate of change at that input value. Okay, so both of these things tell you take a derivative. Okay, these are pretty much how take a derivative is going to show up in a word problem. Okay, most word problems aren't going to ask you for the slope of a tangent line. Okay, that's what I would call a math book problem. All right, but real world problems are going to talk about rates of change and marginal values. Okay, everybody okay with this? Okay with the vocabulary? Okay with the vocabulary?
Yes.
All right, good.
Yes.
Fantastic. Okay, let's take a look then at an applied problem. All right, the production costs in dollars per day of producing X widgets. And again, what's a widget? It's whatever you want it to be. Okay, it's a manufactured product. It shows up in lots of economics and accounting texts rather than saying, I'm producing silicon chips, or I'm producing cell phones, or I'm producing, backpacks, or whatever it is. Okay, so just think of it as a manufactured thing. Okay, so here's my cost. You can see it cubic. What is the marginal cost when X is 175 and when x is 300. Okay, so I'm reading the problem and I'm seeing the word marginal. Okay, and they give me x values. So this means take the derivative, c prime of x, and evaluate it okay, c prime of 175 and c prime of 300. Okay, so that is how I interpret, okay, this question. Does everybody see how I got my words out of this? Okay, the word marginal means take a derivative, and then they're saying, well, what is it when x is 175 and what is it when it's 300? Remember, if you think of the graph of this cubic, it's kind of like hills and valleys, right? So the slope of the tangent line, the rate of change of the output as I go around the curve is going to change. It's going to be different at different values of x. Okay, so that's why I'm going to take the derivative with one of my derivative rules. Okay, that's going to give me the derivative function c prime of x. And then I'm going to find the rate, the marginal, at different x values by just plugging in the x values into the derivative. Okay, remember I said finding the derivative function is actually faster than just trying to evaluate the rate of change at this particular x value. Okay, now do it again at this particular x value. Do it again. I'm not going to keep doing it. I'm going to do it once, and then I'm going to plug in the x values. Okay, so again, what I'm going to do first is take the derivative c prime of x. Because this function is cubic, I can use the power rule for taking a derivative over and over and over again. Okay, so that's going to be bring down the exponent, multiply it by the coefficient that's already there, okay, and then drop the exponent by 1. Okay, now again, if I show more steps than you would show, that's fine. Okay, I'm trying to show as many steps as I can so I don't lose people. All right, but don't feel you have to show as many steps as I'm showing. The first thing I notice here is 1750 is a constant, so that gives me a 0 in the derivative. Okay, the next term is 6x to the first, bring down, if you pull out the 6, bring down the exponent, drop the exponent by 1. Okay, this is meant to be a plus. I'm not sure if it's a plus or a minus. Let's make it a plus. Okay, it's a typo. Let's make it a plus. Okay, so then I have a plus. I'm going to bring the coefficient through. Remember, you don't do anything with those. Just pull them through. Bring down the exponent, drop the exponent by 1. Okay, and then the last term, I'm just going to copy that coefficient, bring down the exponent, drop the exponent on x by 1. Okay, that is the calculus step. Okay, there were 2 bits of calculus I had to do to answer the question. I had to remember marginal meant take a derivative, and then I had to use the power rule to actually take the derivative here. The whole rest of the problem is algebra. Okay, so let's simplify what I have here, because I'm going to plug values into it. So I want to get rid of the stuff I don't need. Okay, I don't need to add a 0. That doesn't do anything. Okay, then 6 times 1 is 6. X to the 0 is 1. So that first term becomes a 6. Okay, then I can multiply the 2 times the 0.04. And again, feel free to use a calculator to do arithmetic. Don't do it in your head. Okay, so 0.04 times 2 is 0.08. X to the first is just x. It's not conventional to write 1 as an exponent. And then this 3 10,000ths times 3 is going to give me 9 10,000ths. X. All right, so there is my cleaned up derivative. Okay, but that was just all algebra. Okay, actually most of it was arithmetic. Okay, now what I need to do is evaluate. Okay, so I'm taking the derivative, and every place I see an x, I'm going to put in 175. Okay, and again, you can do this on your calculator of choice. Okay, it's possible to do this on the Web 2.0 calculator, which I have up over here, which of course now I'm having trouble accessing. Give me a sec. And if I can't make my bar go away, I will just use my TI. Okay, so here is my Web 2.0 calculator, and I would just type that in. Okay, and again, there's a square key. Okay. All right, and if you look at this rounds to 47.56. Okay, so I'm going to go back to my notes. Of course, use a TI if you have it. If you like using it. Again, you have a link to the Web 2.0 calculator in your Canvas class down in your online tools section. So, or, just use that if you don't have a TI. All right, and then they want us to evaluate it at a different value. All right, so evaluated at 300. Okay, and again, we're going to do it exactly the same way. Okay, and I'll just share this with you. Okay. Now, what's important in order to answer the question, because remember, there's two parts to the question. The second part to the question is asking you, what does it tell you about production costs? Well, let's put some rates in the derivative, okay? The derivative has output units in its numerator, okay? So in this example, what are my output units? What are the output units? What are we measuring our output in? Okay, it is called cost, yes. C of X is our output. And what is it measured in? Okay, what is it measured in? Dollars. Okay, they say it right here. Okay. Technically dollars per day, but let's just keep it in dollars. Okay, and what's the input units? Okay, your input value is X. Measured in what?
Would it be production costs?
Nope. Costs are your output. Okay.
Per day?
What's X measured in?
Per day?
Take a look up here.
Okay.
Widgets. Yeah. Measured in widgets. Believe it or not, don't feel, don't worry about it, okay? This is something that isn't typically stressed because application problems aren't typically stressed. But let's be honest, that's what you're going to do with this stuff, okay? We can leverage a lot of the calculations onto computers and things, but you have to be able to interpret it. So again, don't worry about it. It's that it hasn't been stressed. That's why it's strange. Okay. So my input is X, and X is measured in widgets. Okay, so everybody good with that? Output, C of X, is measured in dollars, and X input measured in widgets. That means these numbers that I got when I took the derivative have units, dollars per widget. Okay, and this is also in dollars per widget. Okay, now you kind of need those units to answer the second question, right? These are marginal costs. Yes? Okay, so what does it tell you? What does it tell you about how production costs are changing?
As production reaches 175 widgets, the average cost is $47.56 per widget.
Mm-hmm.
And then when production reaches 300, it costs $111 per widget.
Okay, think of it as if you were to make the 301st widget, your production costs would go up $111 per that widget. Okay.
Okay.
If you're at 175 and you make the 176th widget, your production costs will go up $47.56 per widget. So what's happening to your production costs as you make more? The marginal cost is going up by a lot. Okay? Everybody understand that? Okay, so basically, as production level increases, the marginal cost goes up a lot. Okay, a lot being a technical term. Okay, you can see the difference here. Okay, I didn't quite double my production level, but I more than doubled my marginal cost. Okay, everybody comfortable with that? And in case of, again, I know accounting folks are looking at this saying, I've never seen C of X, right? I just have columns of numbers, okay? Take my word for it, you could develop a C of X from your columns of numbers, okay? If you have a lot of cost data, historical cost data, okay, you can use a regression to build a function, okay? Usually in accountancy, we're not using derivatives and things to find these questions, answers to these questions. You use a lot of like accounting rules and arithmetic. It can be done this way too. This way is more of an approximation, okay? But again, think of it in terms of like financial models on Wall Street with, say, millions of data points, okay? We're not going to do millions of number crunches. We're going to put them in a function and approximate them that way, okay? Nowadays, we're doing big data, machine learning type things, so this is changing yet again, okay? Please realize that the science of manipulating lots of data is something that constantly changes, okay? And be open to learning new ways of dealing with it, okay? But let me ask at this point, any questions about this one, this example? Anybody have a question about this example?
No questions for me.
Okay, great. Okay. The second example is real similar. Okay, so I'm going to ask you to try this one. Okay, so you try number 3. Okay, I'm going to help you set up, right, the problem before I turn you loose on it. You can again see marginal cost. Okay, this is done exactly the same way as the first problem. Find C prime of X, evaluate C prime of 200 and C prime of 500. Okay, so same exact overall strategy. What you might not be comfortable with is taking the derivative, although this is not that weird of an equation. Let's do a little bit of algebra on it first, so we make it a little bit easier to deal with. Okay, nothing I can do with 200, it's a constant. 0.05x to the first, you know that. And I'm going to rewrite this last term as 10,000 x to the minus 1. Why am I doing that? I'm using a rule of exponents that says 1 over x can be written as x to the minus 1. Okay, let's just take a look. This term you can think of as this way, 10,000 times 1 over x, and then the x, 1 over x, is x to the minus 1. Okay, you need to get really comfortable doing this quickly, okay, before you actually try to take a derivative. Okay, if you see a single term like an x or an x squared, you can rewrite it with a negative exponent up in the numerator. Okay, so now that we did the algebra part here, you try number 3 and type done, and you finish. Okay, and again, guys, feel free to talk to each other in the chat. Okay, I'm not going to always jump in if you want to talk to each other. That's fine. You would be doing that in a normal classroom, so feel free to do that. It'll take maybe about 5 minutes for this one. We'll take maybe another minute for this. Just see if you can get through the calculus and the evaluation part. Okay, folks, I know not everybody's finished, but I'm asking a question of the people who got this far. What value did you get for C prime of 200? Can you put that in the chat or say it out loud? What did you get? Yep. Okay. All righty. Anybody else get the value that's in the chat? Anybody else get that? Okay. Well, let's work through the example. I'll try to pick up the pace so it isn't super slow. All right, I'm going to differentiate my original cost function to find the marginal cost. The 200 gives me nothing. Okay, so I'm not going to write the 0. Okay, and again, since this is 0.5x to the first, this is going to become 0.5x to the 0, which is just 0.5. Okay, so notice constants disappear. Okay, x terms become constants, and you drop the exponent value on all the other terms. Okay, so let's take a look at this other term. I have 10,000. I bring down the -1, and I subtract 1 from an already negative exponent. Okay, so if I simplify the derivative, this gives me 0.5. -1 times 10,000 is -10,000. And the x to the -2 can go in the denominator squared. Okay, so this step's the calculus step. This is just algebra using rules for exponents. Okay, then what I'm going to do is plug in my 200. Okay, and then you can evaluate that on a calculator. I'll bring up a TI-84. Let's see, this is stuck in the middle. Okay, that should be fine. Let me share my TI with you so you can see it. And again, I kind of deliberately switch between different tools so I can hit what everybody is interested in. So let me turn it on. Okay, so this would be 0.5 plus, and then it can be 10,000 over 200 squared. I like using my fraction template, which is alpha, y equals, and then pick the first one, numerator over denominator. That saves me worrying about how to parenthesize a fraction. Okay, and then this is 200 squared. It kind of looks just like what I have on my paper. Okay, and again, this is a minus, not a plus. Let me go back and change that to a minus. Okay, so there's the 0.25. Okay, so I have 0.25, and my output units are in dollars, and my input units are in widgets. Okay, so I could say $0.25 per widget, but again, we don't normally describe it like that. We'll say 25 cents per widget. right? So my marginal cost when I make 200 of these things is 25 cents to make the 201st widget. Okay, if I evaluate this at 500, okay, I can go back into my TI and just say second entry. Okay, that'll type the last thing I entered. And all I have to go in and do is change the 2 to a 5. Okay, and that gives me 0.46. Okay, and to interpret the results here, yes, you could say if I were to make the 201st widget, my cost would go up by 25 cents. If I were to make the 501st widget, my cost would go up by 46 cents. So marginal cost is increasing, but slowly. Now, again, slow may be a relative term. Okay, because again, it almost doubled, but I more than doubled my production level. So I'd say it's not increasing terribly fast. Okay. So here were 2 examples that were almost identical. Okay, let me get the calculator out of the way. And let me just ask any questions about either of these. Okay, and I'm interested in the folks who aren't saying anything. Okay, you're the guys I'm interested in what you're thinking. Okay, so everybody okay with this? Especially my quiet friends. Okay, please ask if you've got questions about anything, or if you're not comfortable asking now, at least reach out to me later and say, hey, when you did that example with production costs, I didn't understand this bit. Okay, one thing about being confused is it hardly ever gets better on its own. I mean, you can work really hard to try to get yourself clearer on a topic. That's fine, but sometimes asking a question is the quickest way to get it cleared up. Okay. No questions? Then what I want to show you are some other, what I'm trying to do is to show you some basic business stuff. Okay, so this one's a little bit different. Okay, I have same old C of X production costs in dollars per week of producing X widgets. So yeah, input X in widgets, C of X output in dollars. Okay, or dollars per week. Okay, so technically our units would be dollars per week per widget. Yes, absolutely, you're right. Okay, so let's talk about this. Okay, we've got a cost. Now look at this piece, the demand function. Okay, and let's talk about demand function. P of X is a price in dollars. X is widgets. Okay, so again, for those of you who've taken some econ classes or just general business stuff, you probably realize your price is dependent on your demand. Okay, so widgets demanded, let's say that. Okay, but in any event, it's widgets. Okay, so what you have here is an equation that gives you price. Okay, it's a price. And they're asking you, look at what they're asking you for now. Marginal cost, okay, we can do that. We kind of know how to do that. We just take the derivative of the cost function. But then they're asking for marginal revenue and marginal profit. Okay, so I'm pretty sure I can do the cost part right away. Okay, I just differentiate costs, plug in 200 and 400 into my cost derivative. But I need to know about revenue. Okay, so somebody tell me in words what revenue is. Okay, so what's revenue? I want to make sure we're all on the same page. We're working with the same definitions. Tell me in English, what's revenue? Somebody want to just unmute yourself? Nobody? No counting majors? Nobody? Money coming in. Thank you, Ryan. Okay, money coming in. All right. My next question is the money you get from selling. I was going to ask you, where does this money come from? So Nia's already ahead of me there. Okay, money coming in from selling a product. In this case, we're selling widgets. Okay, so that's what revenue is. We know the price for a widget, right? Okay, price is P of X. Okay, so what's the relationship between revenue and price of the product? What's the relationship between revenue and price? Because they gave me price. I'm kind of itchy to do something with this price here because I can't see any other reason to have it. What's the relationship between revenue and price? Well, how about a thought experiment? Okay, imagine we're selling bananas. Okay, and let's say bananas are 10 cents a piece. Okay, and let's say I sell 8 bananas. What's my revenue? Okay, they're 10 cents a piece. Yeah, okay. So if bananas are 10 cents a piece, okay, and I sell 8 of them, okay, you're saying my revenue is 80 cents, right? Because bananas are sold in cents. How'd you get that value? How'd you get 80? What did you multiply? Okay, okay, I see it. Okay, price times the amount sold. Okay, multiply the price is 10 cents with the 8 bananas. Good. Okay, so revenue is price times amount sold. Okay, so that's my P of X times X, right? X is the quantity demanded. And that's 250 plus 0.02x minus 0.0001x squared times the P of X times X. Okay, you can look at this and realize, oh, all I have to do is bump up the exponent on X in each term. And the 250, well, that's 250x to the 0, so that becomes 250x plus 0.2x squared minus 0.123x cubed. There's my
That's
revenue.
add zeros in that
Two
last term.
zeros in the last term. 2 zeros. Thank you for pointing that out. That would have made things nasty. Two zeros after the decimal point. Thank you. Okay, so here's revenue. And I can write that as R of X. Okay, because it's a function of X. All right, so do you understand how if they give you a price, just multiply your price equation by X to get your revenue? Okay, and then if you want your marginal revenue, okay, marginal revenue is R prime. Okay, so again, I think we can do the C prime pretty easily. Okay, and then I have my R prime, which oddly enough is going to give me back what I kind of started with, sort of 250 plus 0.02 times 2x minus. Okay, so here's my marginal revenue. And again, I just did the power rule on it, right? So here the x went away. Here I'm bringing down this 2, dropping my exponent by 1. Here I'm bringing down the 3, dropping the exponent by 1. I'm going to start picking up the pace on those because, again, it's not hard. It's just that repeated process over and over again. And then the algebraic simplify step. Okay, so there's my marginal revenue. Okay. Again, marginal cost, we can kind of do really quickly up here. Okay, the 4,000 gives me a 0. Okay, I'll wind up with negative 32 from the 32x plus okay. So again, C prime of x, I'll write it down here. I'll make my notes a lot clearer when I upload them, sorry. So here's our marginal cost. So I'm just doing the arithmetic on this big gnarly thing here. Okay, so here's marginal cost. Here's marginal revenue. Okay, so what I can do, they're telling you what are the marginal cost and marginal revenue when x is 200 and when x is 400. So that's just a plug in 200 into my marginal cost and plug in 400. Okay, that's not even calculating, that's a calculator problem. Okay, so just everywhere you see the x, you're going to put in 200. Okay, when I did that, I got $7.20 per widget. Okay, and when I put in the 400 into my marginal cost, I got $80 per widget. Okay, so you can see the marginal cost goes up quite a bit, okay, as I make and sell more of these things. Okay, same idea with the revenue, R prime of 200 and R prime of 400. Again, I'm just taking this derivative that I calculated, okay, and plugging in the different values. So this is going to be 138, and again, dollars per widget. Okay, and negative 214 dollars per Okay, so it looks like as I make more, as I go from making 200 to 400, my cost goes up significantly. And look at what happens to the revenue. The revenue drops. Okay. Now, what they asked you also was to find marginal profit. Okay, so you might remember profit equals revenue minus cost. Okay, and it turns out with marginal profit, I don't have to do the calculating all over again. I can just use the marginal values I got. Okay, so in other words, you don't have to build a profit function and differentiate it. You've kind of gotten these two already. Okay, how would you have negative dollars? Okay, this is true. I guess what it's saying, what you're saying is, how could you lose money on revenue? I understand what you're saying, but just think of revenue here as a component of profit. Okay, so in other words, the only revenue is only a positive thing normally, but you could think of it as, well, maybe people start returning your goods or something like that. So think of it mainly as a component of profit that's negative. Okay, think of it as a component for profit. But yeah, you're right. In normal accounting, this isn't a negative number. Okay, but just look at it from the point of view of the example here. Okay, so if I want to find out what my profit level at 200, I'm going to put in the revenue value for 200, which is 138, minus the cost. Okay, so I get an increase in profit of about $130.80 per widget. Okay, at that production level. At the other production level, which was 400, I'm going to take the revenue, which was minus 214, and then subtract the cost. And again, what that's telling me is I really don't want to make and sell that many because my profit kind of plummets. Okay. So again, basically, I'd say stick to the lower production level. Okay. Again, I'm not as savvy in all of the different accounting situations where possibly revenue could be negative. So I apologize for that. I can think of like refunds or stuff like that that might, kind of make it like you're losing money instead of taking it in. But again, I don't have a strong accounting background in order to answer that. But basically, if you just look at the numbers here, what I'm trying to show you is you can use the rates here to find the marginal profit. Okay. What's more important to understand from this example, rather than the wonky numbers that came out of it, is if they give you a price times number demanded is your revenue, and then profit is revenue minus cost. Again, I want to just make sure everybody is comfortable with those basic equations. Okay, so everybody comfortable with the basic equations used in this example? Good.
Yes.
Fantastic. Let's get away from profit and stuff and look at a different type of example. Okay, because again, we may see different types of examples in whatever we're working with. Maybe we'll work in social science and demographics are going to be part of what we play with. The United States population is becoming more diverse based on the US Census population predictions for the years 2000 to 2050. The projected Hispanic population in millions of people can be modeled by this exponential function. Okay, so what they're telling you is a couple of things. They're telling you, first of all, that your output H of T is Hispanic population in millions. So basically what that means is if you see a number like 37.791, that means 37,791,000 people. Okay, it's a scaled value. Okay, that's how many people we're starting with. Okay, and T is years since 2000. Okay, so you're not ever going to plug in the year number 2000. Okay, the year 2000 is your 0 year. Okay, year since 2000. Okay, you can think of it this way. Here's your model. Okay, this is your starting value. So this tells you the Hispanic population in the year 2000 in the United States, 37,791,000 people. Okay, this is the growth rate. Okay, see the numbers after the decimal point? So the population is growing on average about 2% per year for every year after 2000, 2.1%. Okay. T is going to track how many years since 2000. The model is only good for 50 years. Okay, so what the Census Bureau is telling you is don't use this model outside the range of 2000 and 2050. Okay. So how could you figure out average rate of change? Okay, well, if you want to know the average rate of change, okay, average rate of change, take a look at that word. I'm going to highlight average. Okay, what's average rate of change? Between two input values. What's the average rate of change between two input values? How do I do that? Anybody have any thoughts? Anybody remember from stuff we did prior what average rate of change? Yay, okay, yes. Okay, average rate of change is the slope of a seat count line between the 2 points. What 2 points? So what 2 points do I use? Okay, feel free to talk if it's too tedious to type it all. What are my 2 points? Okay. Anybody have any other thoughts? Remember, your points are going to look like this. Okay, your first point is an input value. Your second coordinate is an output value. Okay, and we said our input values are T values and our output values are H of T values. Okay, so output, input. Okay, so you're right in that 20 and 30 are part of this. right? 20 years after 2000 is the year 2020. Yes. And 30 years after 2000 is the 30. And as you can see in the chat, we need the H of T values that go with. Okay, so all I need to do is evaluate H of T at the different T values. So I take this right-hand side and I evaluate it when T is 20 and when T is 30. I'm going to do it two ways. Let's do it on the Web 2.0 calculator. Okay, so that's 37.791, 1.021. And then I want to raise that to the, okay, see the raised to a power x to the y. The first one's 20. Check that it looks like what you expect up here. Okay, so that's 52 point, let me round it to hundredths, 57.27. Okay, everybody see how I got that? I just plugged in a 20 for my T value and I got the H of T that went with it. Okay, so this is going to be 57.27. Okay, and then I'll do the other one on the TI, so folks that have a TI can see how that works. Okay, hopefully you can still see the TI. I'm still sharing that with you. So again, that's going to be the same model, 37.791 times 1.021. Okay, and on the TI, here's how you raise to a power. You put 30 in for your exponent. And again, that one is 70.50. I'm going to round. Okay, everybody see how I got the HT values for 20 and 30? Okay, so then I just take slope, or average rate of change, I guess I should say. Because they didn't ask me for slope, but that's what I'm going to use. Okay, so I'm going to take the difference of my output values on top. And divide that by the difference in the corresponding input values on the bottom. Okay, and again, you can do this rather nicely on a TI. If you do this on the Web 2.0 calculator, please parenthesize the numerator, parenthesize the denominator. Okay, so the calculator will do the subtractions first and the divide last. Okay, so here, if I'm going to do that type of a calculation, I'm going to use my fraction template, alpha y equals, and then put the 70/50 first, minus the 57/27. And in the bottom, I have 30 minus 20. And that gives me 1.323. Okay, now I have to worry about units. Okay, my output units are on top, and that's going to be million people, okay, specifically million Hispanic people. And the bottom is in years. Okay, so that's saying what? It's saying on average, between 2020 and 2030, the Hispanic population in the United States is projected to increase, because it's positive, by about 1,323,000 people per year. Okay, 1.323 million people per year. Okay, everybody see how it was done? Questions on how it was done? Okay, so again, this is a rate. It has units in it. Okay, now this is on average over a 10-year period. Okay, suppose instead we want a snapshot at a particular value, instantaneous rate of change. Remember, this is another word for derivative. And another dead giveaway is they give you one t-value, not two. Okay, so they give you one t-value. So what this is saying is estimate the instantaneous rate of change. This says find h prime of t and then evaluate h prime of 20. Okay, now that will give you an estimate of the actual rate of change in the year 2020. In other words, on average, you're approximating, okay? So it's still an approximation, but it's not as gross an approximation, okay? Because this is over, on average, over 10 years. Period. On average over the 10-year period, okay? This is a finer estimate right at 2020. So you could think of it as on what do they assume the population change will be going from 2020 to 2021. Okay, and this problem was written long before we got close to 2020. So I realize this is historical data now. But let's take a look at taking the derivative. Okay, I have an exponential function. Let me just write it again down here so everybody can see what we're working with. Because again, exponentials, for some reason, folks are not quite as comfortable with them. Okay, so here's my exponential function before I take the derivative of it. So this is just h of t. Okay, now the 37.791 is just a coefficient. So I'm going to pull that through. Okay, my base is the 1.021. So remember how you take the derivative of an exponential, you say ln of the base. Okay, and then you multiply it by the original exponential, 1.021 to the t. Okay, so this part over here is the derivative, ln of the base times the original exponential. Then all I need to do is evaluate this at 20. So wherever I see an x, I'm going to put in a 20. Okay, just so you remember, this number out here as well as the ln, okay, these are both numbers. Okay, there's no variables in here at all. The only variable part is here. Okay, so if I want to evaluate this, I'll do this on my Web 2.0 calculator. Clear that. And that is 37.791 times, again, ln is in one of these drop-down boxes, ln 1.021 multiplied by, and then my exponential base is 1.021 raised to the 20th power. Okay, and just double check that that looks like what you've got written down. And that gives me about 1.19 rounded to hundredths. Okay, and that's million people. Because it's a rate just like the slope was. Okay, so again, on average, over the 10-year period between 2020 and 2030, we're seeing a larger rate of change. Okay, so here, going from 2020 to 2021, we're approximating a change of an increase of about 1.19 million people, or 1,190,000 people. The fact that this number is higher kind of tells me maybe these rates are going to increase as the decade progresses between 2020 and 2030. Okay, so this is for 2020 into 2021. Okay, like a marginal rate. Okay, and this is an average over 10 years. Does everybody understand the difference? Everybody understand the difference? Again, if you're looking at demographic data and you're modeling it with equations, sometimes it's important to understand the nuances of what it's telling you. Anybody have questions about this one? Are we good? Okay, so could you just give me a shout out, yes or no? Are we good? Any questions?
No questions for me.
Awesome, thanks, Cornella. Anybody else? How about the rest of you? Okay,
Nope, I'm good.
we're good. Okay. So again, I took a lot of time on the applications because I wanted to make sure folks are comfortable with them, because usually applications are things that get people a little bit upset.